Okay, here in 5.4, we're going to go back to the question of the exact area between a curve or a function f of x starting at a, ending at b, the area between that function and the x-axis between those two vertical lines. So our goal is to develop a quick method to find such an area for any function. So we looked at the indefinite integral with antiderivatives back in 5.1. We took it a little bit further with u substitution in 5.2. Turns out we're not going to talk about 5.3. That kind of does some applications of these things that is not necessary in our course. So we're skipping 5.3. And we're in 5.4, we're going to investigate these things called Riemann sums. So it's going to come to a climax in 5.5. It's all going to come together. We're going to figure out how this exact area connects with antiderivatives. But for now, we're going to leave antiderivatives. We're not going to do any of those indefinite integrals or anything like that in this section. In 5.5, what we're going to learn here is going to meet that stuff. So what is this thing called a Riemann sum? So Riemann is a German guy, and well, he developed this stuff. So let's take a look. He said if you want to find the area between a function and the x-axis from a to b, well, let's get some building blocks before we dive into finding the area exactly. In this section, we're going to approximate that area. Okay, so how are we going to do that? I'm going to show you some drawings here in a moment. We're going to approximate this area using the areas of rectangles. The simplest two-dimensional shape, you might say, is the rectangle. Let's take a look. So imagine I've got this drawing a second time, right? There's my f of x again. There's my a and my b. Let's say I wanted to approximate the area between that function and the x-axis. So what I'm going to do is draw several rectangles. Just as an example, I'm going to use 4. So I'm going to split this interval from a to b into 4 equal parts. So I'll divide it in half, then I'll divide each of those in half. Okay. Then for each of those columns, I'm going to create a rectangle. And the way I'm going to do it here, I'm just going to look at the left side of each column. So my first column here going up the left side, where does it meet the function? And that's where I'm going to make the height of my rectangle, like so. And I'm going to do that for each one. So there's the first column with the height on the left side. Then I go to the next column, and where does the left side meet the function? I'll make my rectangle there. And the next one is going to be here. And the very last one actually falls below. And so we're going to think, okay, if I was to find the areas of these 4 rectangles, that wouldn't be a bad approximation for the exact area under the curve. Now, obviously, I'm going too much here. I'm going over, 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 and here a little bit under. So maybe like these two balance out, but then these are definitely over. Well, I've got an overestimate of the actual area, but not a bad approximation, and I could find the areas of these rectangles pretty easily. So we're going to give this style a name. We're going to call that left rectangles because we took the heights on the left side. And we're going to denote that L sub n, capital L sub n. What is the n all about here? So L for left, but the n, that's the number of subintervals. The subintervals are the little sections. So here we had 4 of them, 1, 2, 3, 4, which also means there are 4 rectangles. Okay, we'll see that in an example shortly. I want to show you another style also. We get 2. I've got the same drawing again, f of x and a and b. I'm going to split this into 4 pieces one more time. 4 is an easy number to work with. We could divide it into any number of subintervals. Okay, now this time for each column, we're going to make the height on the right side. So going up that first column, where does my right side meet the function? And then we'll do it again here. Where does that meet? And here. And finally, that last one spills over just a little bit. Now we're going to find the areas of these rectangles. And that would be another way to approximate the exact area. Okay. So you can say, well, we were a little bit under here and under and under and then a little bit over. You know, maybe in this case, these guys balance out pretty close, but then we're definitely under overall. Well, all right, we know we have an underestimate, but not a bad approximation this way. We're going to call this, you guessed it, right rectangles. And we're going to denote that capital R sub n, where n again is the number of subintervals. In this case, still would have been 4. Okay, let's check out some examples. Here we go. We're going to look at 2 different versions here. So approximate the exact area using the Riemann sum. We're going to look at f of x equals x squared plus 1 from x equals 0 to x equals 8. So we'll graph it in a moment, but maybe you can imagine that parabola and its starting and ending points. Okay, so for part A, we're being asked for L4. 4 again, nothing special about 4. We could use any number there. We'll use other numbers in later examples, but okay, the left rectangles, we'll do 4 of them. A quick sketch is helpful. So here I've done a quick sketch of x squared plus 1. It's the parabola just shifted up by 1, right? So if you remember that it's that parabola shifted up by 1, that's going to be helpful. If not, hey, you know, if you want to graph that, you can use Desmos, the Desmos website. Really helpful in those cases. Okay, and then I'm just going to go ahead and draw those rectangles. So I'm going to draw, you know, this line here at 8, and my other line is at 0, and it's in 4, so I'll divide in half and then divide each of those in half. And then I'm going to indicate where all of these occur. So this one's at 0, and then at 2, 4, 6, and 8. Okay. Okay, then they're asking, so that's the 4, then we want the left, so we'll draw the heights there on all of the left sides, and my drawing is not perfect, but I think you get the idea. We're going to find the areas of these 4 rectangles and add them together, and that's going to be our approximation. Literally all we're doing is adding the areas of rectangles in this section. Okay, so let's find the area of each one. We'll add them all up. So we're going to say, okay, L4 is going to be equal to this. So I'll talk you through this step. The first rectangle, think base times height. So the base of that rectangle is 2. The height of that rectangle on the left side is 1. So 2 times 1 is the area of my first rectangle. The second rectangle, well, the base is 2. This time the height is 5. How did I get the height to be 5? Well, definitely not based on my drawing, but I can plug 2 into the function, right, to tell where it would be on the y-axis. So 2 squared plus 1. There's my height of 5. Definitely not clear from my drawing. Okay, the third rectangle, well, again, a base of 2. And this time a height of 17. If I plug 4 in, 4 squared plus 1, that's where I get the height of 17. And the fourth rectangle, base of 2. And because it occurs at 6, the height is 37. And you notice we don't care about the height at 8 because, well, that was on the right side of our last rectangle. So it's only at 0, 2, 4, and 6. Those are our 4 heights, just like that. Multiply these all together, add them up, and you will get 120. So that is our L4 approximation for that area. Okay, let's look at another one. We'll mix it up this time. Same function, still from 0 to 8, but now we're going to do R8. So I've just sketched that function again. It's at 8 there. Why don't I go ahead and draw that line? Of course, I know it crosses here at 1. Now I need to draw 8 little rectangles. So here's the one in the middle. I'll divide that in half and that in half. Then I need to divide these all in half again. And there are my 8 columns. Where do these all occur? At 1, 2, 3, 4, 5, 6, 7, and 8. Okay, and then we're doing the right rectangles. So on the right side, and my drawing is definitely not big enough or to scale, but you get the idea. So there's the first one, second one, third one, fourth, fifth, sixth, 7, and 8. Okay. So just like last time, I'm going to find the base and the height of each rectangle, add them all up. Well, I've already done that. Here it is. Let's see if we can fit it all on the screen. I think we can. The base of every rectangle is 1. So 1's all the way down, right? And then the heights occur on the right side. So the heights occur at 1, 2, 3, 4, 5, 6, 7, and 8. We don't include 0 this time because we're on the right side. So the height at 1 is 2. The height at 2, why do I have 10 there? That's interesting. That should be 5. Okay. Yeah. The height at 3. There's the 10. I think I was off by 1. So I got 1, 2, 3, 4. At 5, it's 26. Aha, I missed that one. That's what happened. So we got 1, 2, 3, 4, 5, 6, 7, and then I need one more. 1 times, and at 8 it's 65. Okay, so I think probably have a flaw in my final answer there, but do we have 8? 1, 2, 3, 4, 5, 6, 7, 8. Put those all together, and don't think it's going to be this number. Let me grab my calculator. $212. I had 207 before because I was missing the 1 times 5. Okay, got a little bit off screen there. There's R8 in this case. So a couple questions, or a couple of things we can reflect on. You know, we can tell our left approximation was an under approximation because we've got all these gaps here, so that we know that's definitely too small. In a similar way, The right approximation in this example we know is too big because all of these hang over a little bit. So we know that number is bigger than the actual exact area. But that said, this one too small, this one's too big. Which one is closer to the exact area? And you think, well, these gaps seem bigger than how much these hang over. And yeah, I mean, R8 is going to be closer, even though it's a little bit too big, it's going to be closer to the actual answer. And so maybe then the question becomes, well, is it always better to use more subintervals? 4 versus 8. And yeah, the more you have, the more accurate it's going to be because it diminishes those little bits of error, whether above or below. If you have more subintervals, it's always more accurate. Okay. Not that we really need to know that at this point, but we can definitely tell that that's true. Okay, let's stop this video here. We're going to do some applications in the next one.